showing one bond, so two other things can go to him. So all four of your amides have to look like that. The only way in which they can differ is, those three things onto the fundamental part that's an amide. So all four of them have to contain that amide functional group. Total of 3 carbons. So here's 1. So 2 more carbons. Maybe they both go there, meaning these have to be hydrogens. Maybe they both go there, meaning this has to be a hydrogen. Maybe one goes there, meaning this has to be a hydrogen. And there could be an ethyl group on here, meaning these are both hydrogens. So those are the 4 possibilities. And if you throw in the hydrogens that I didn't include, it'll total 7 hydrogens in all these cases. So those are the 4 amides. And then the second part of that question says, one of these has a much lower melting point and boiling point than the other 3. Which one is it? Well, it would be this one, because it's the only one that's not capable of hydrogen bonding. The others all have hydrogen covalently bonded to nitrogen. That allows for hydrogen bonding. That one does not. And I think, I don't want to say this. I guess I'm not sure if I should be saying this, because I'm not sure if it's true or not, but I think I took this one homework. This question. Okay. I'll just check. Maybe I did. Did I? I think I did. I might not have. Let's see what else we got. A lot of you didn't have the conjugate acid of the amide ion. You were given that, and it asked, what's its conjugate acid? Well, if this thing grabs a proton, something is going to get ammonia out of the deal. Hydrogen forms a bond here. Positive charge hydrogen cation. No longer have a charge. So take this guy, stick a proton on it, so ammonia is the conjugate acid of the amide ion. On the acid-base reaction with that alkyne, the given alkyne was that, and we were reacting it with sodium hydride. I wrote the sodium hydride on the paper as NaH, but that's what it really is, sodium ions and hydride ions. A number of you somehow knew that this was going to be an acid, somehow knew that it was going to donate a proton, somehow knew that it was going to be, therefore become anionic, but you put the charge on this carbon. Quite a number of you did that. This is the acidic proton. The acidic proton is going to be one that is bonded to an sp hybridized carbon. Hydrogens bonded to an sp3 hybridized carbon are about as unacidic as protons go. So this is the proton that hits the road. giving us that. Of course, sodium ions aren't doing anything, they never do anything. Hydride grabs the proton to give molecular hydrogen. What else we got? And nothing else was jumping out at me as problematic. I've heard from post-test conversations that a lot of you didn't like the very last one, ethyl cyclohexane. Most of you put that no, it can't be cis-trans. But a lot of you seem to think that was, I don't know, bothersome. If there's only one thing, you can't have cis-trans. I guess that's the bottom line there. Anything else here anybody want me to go over? Talk about? Anybody want to complain about anything? Not that it'll do you any good, but sometimes it makes you feel better.
Yeah. I want to feel better. Oh, could you draw out 13? It's the cis-1 terbutyl. It's number 13.
13.
It's cyclo.
Okay, yeah, 13 says draw the most stable conformation of cis-1 tertiary butyl 4-methyl cyclohexane. As soon as you see cyclohexane, you know that the most stable conformation has got to be a chair. So step one is draw yourself a chair. Most of your chairs were pretty good. Some of your chairs were pretty funky. If I circled something or put a little question mark by it, it meant that I spent last night in between the innings of the baseball game stroking my beard trying to figure out what you were drawing. So if I did that to you, if you don't see why your chair is funky, you might want to come and see me and we'll straighten out your chairs. Anyway, there's a chair 1,4, so pick any carbon. It's helpful to do this guy. Call that 1. That would make this guy carbon 4. Here's one funky thing that some of you did. Like up here on carbon 1, you had somebody going out this way. Especially if that's sitting by itself. First of all, it's kind of, I don't know what it is, but when it's sitting there by itself and I'm not seeing the other position, I don't know if you meant it to be axial, especially some of you did something like this. That was even funkier. You had a little bit of an angle to it. Did you mean that to be axial and you just didn't draw a very vertical line? Did you mean it to be equatorial, where traditionally we would show it going that way, but you had it going that way? That usually warranted a question mark, but I saw that. Anyway, here's 1,4, tertiary butyl and methyl, and it's got to be cis. So on the same side. So if we put it on the uppermost here, then it would have to go on the uppermost here. That would be on the same side. If we put it on the lowermost here, then the other one would have to be on the lowermost here. That would be on the same side. And what you notice is that there's no way for both to be equatorial. A lot of you are really trying hard, since you asked for most stable conformation, to put everything equatorial. Well, you simply can't. If it's a cis-1,4 molecule, that geometry is not available to you. If we put something in the equatorial position here, in order to be cis here, it's got to be axial. So there's no way around one being equatorial and the other being axial. So we're going to want to put the tertiary butyl group, i.e. the bulkier thing, in an equatorial position the methyl group therefore in an axial position. Now that, your answer, your correct answer didn't necessarily have to look exactly like that. You could have put your tertiary butyl group here, your methyl group here, that would have been fine. You could have chosen two other carbons to be 1,4, your 1,4 carbons, as long as you had them in a 1,4 relationship. Okay, civics question. I know a couple of you know the answer because I told you, so if I told you, don't answer. Civics question. I'm a U.S. citizen by birth, but I was not born in any of the 50 states. Where was I born?
DC.
Puerto Rico. They're all good answers. But I often ask this question. I get Puerto Rico, I get Guam, I get some sort of overseas military base. I was born on a ship at sea. I get all sorts of things like that. And rarely, I heard one answer, that's because we talked about it. Rarely does anybody respond what is the most dominant, by far, answer to that question. And that's that I was born in DC. People on this side of the country don't appreciate the fact that DC is a stateless entity. Don't get to vote for Senate. They get to vote for a representative in Congress, but that person can't vote while in Congress. People don't appreciate that. What made me bring it up today is that the Nationals won last night. So go DC.
Now the Mariners are the only team in Major League Baseball history to never reach the World Series.
That's absolutely correct. The only team that ever did it. Okay, and baseball's going to come up in a few minutes today too. Again, because you guys gave such great answers to the baseball question on that quiz. You gave such great answers, as in only 3 or 4 of you. Only 3 of you put an actual baseball team down.
What if they had science and geography?
Okay. We need to talk more about isomers.
Yeah, sure.
We're getting to the fun part of isomers. Constitutional isomerism, child's play. Let's remind ourselves what isomers are. They are
Molecules that have the same exact formula or the same chemical.
the same formula. Yeah, exactly. Molecules that have the same molecular formula but are different. There are 2 big categories of isomers. Constitutional isomers, also sometimes called structural isomers. We've talked about these guys. Constitutional isomers are guys that have the same molecular formula. What makes them different is that they're bonded in a different order. 2 bromopropane as opposed to 1 bromopropane. It's simply a different order in which the atoms are arranged. That is highly logical. Of course they're going to be different molecules if the atoms are bonded in a different order. The other type of isomers are collectively referred to as stereoisomers. They're isomers, so we're talking about molecules that have the same molecular formula, so the same number of each type of atom present. They're not constitutional isomers, which means they're all bonded in the same order, yet they are still somehow different. stereo implying something spatial, something geometric. They're different because of some geometrical reason. We have talked about one type of stereoisomerism, and that is cis-trans. Is a type of stereoisomerism. Cis-2-butene and trans-2-butene, same atoms, bonded in the same order, but there's a geometric difference that makes them different molecules. Okay, among stereoisomers, there are two big categories. Stereoisomers can be either enantiomers, or they can be diastereomers. Here's the difference. Enantiomers are mirror images of each other. Diastereomers are not. Now I know what it says on the board right there, but if I ask you on a quiz or test, what are enantiomers, and you say there are molecules that are mirror images of each other, that will be wrong. I didn't get to this statement until I got down there. They are different molecules that are mirror images of each other. We've already established that they're isomers. Molecules of the same molecular formula but are different. If they are isomers, same molecular formula but different, and they are mirror images of each other, then we've got ourselves a pair of enantiomers. The mere fact that they are mirror images of each other does not make them enantiomers. Most objects and their mirror image if I hold this up to a mirror, sort of ignoring the fine writing, just the basic shape and color of the pen. If I hold this up to a mirror, I'm going to see this. How are they related to each other? They're the same thing. Which was the original object and which was the mirror image? Oh, let me do it again. There's no way to know, because they are the same thing. Are they a pair of enantiomers? No, they're not even a pair of isomers. They're the same thing. They're not part of this discussion at all. And don't go saying that enantiomers are molecules that have mirror images. What's wrong with that statement?
Maybe the same molecule.
Everything has a mirror image. So the mere fact that you have a mirror image, that's not enantiomerism. That mirror image is different from the object that made it. A piece of not very amusing organic chemistry history. There was a time when there was only one organic chemistry textbook that was used literally throughout the entire world. When I was first taking an organic chemistry class, it was the textbook I used. There was a couple of authors named Morrison and Boyd. One of the reasons why I like the Solomon's text is that he was the first to challenge the monopoly that they had. Morrison and Boyd took Solomon's to court and said, hey, your book's a lot like ours. Solomon said, well, yeah, it's because it's organic chemistry, same as yours. The judge ruled, of course, it's going to be similar because it's the same topic, and allowed Solomon's book to exist penalty-free, and that opened the floodgates, and now there are a whole bunch of organic chemistry texts. Anyway, the Morris, so I appreciate Solomon's for challenging the behemoth. Morrison and Boyd's text was famously dry, famously boring, except there was one joke in it. Relating to this, talking about enantiomerism and the whole mirror image thing, saying about things, whether they have mirror images or not, and they said everything has a mirror image, in parentheses, except vampires, of course. And then continued on with the discussion. I said not very amusing. I prefaced it by saying not very amusing. But it was their one attempt at humor in the whole text. Okay. Let's make sure we understand this better. If I hold this pen up in front of the mirror, this is what I see. Same thing. Not enantiomers. Not isomers at all. The most famous example of a non-molecular object that has enantiomeric properties is a hand. If you hold a left hand in front of a mirror, what do you see? You see a right hand. Which is my left hand, which is my right hand? You can tell, right? They are different. Do they have the same parts? The exact same parts. Are they organized in the same way? Yes. I have thumb followed by pointer finger, followed by whatever you want to call this one, followed by ring finger, followed by pinky. Same thing here. I got the palm on this side, the back of the hand, same thing. They have the same parts organized in the same way. Everybody's bonded to the same thing in both these objects. Yet they are different. They are absolutely distinguishable. They are not the same thing. That makes them isomers. They are mirror images of each other. That makes them enantiomers. What is it about a hand that when you hold it up to a mirror, you see something that is not the same as itself? Whereas if I take this pen and I hold it up to a mirror, I see something that is identical to itself. But what about the appendages?
Was attached to.
Branches in and of themselves, no. Yeah, sugars show this property.
Plane of symmetry.
It's all about plane of symmetry. It's all about plane of symmetry. What determines if an object has a mirror image that is identical to itself or different from itself is whether that object has a plane of symmetry. This pen, I can slice right. Plane of symmetry means there's a way to slice this sucker. I can slice it right down top to bottom such that the two halves reflect each other. I can do that with a pen. The fact that I can do that with a pen means its mirror image is going to be the same as itself. If I look at a hand, however, there is no way to slice this thing. And if I just try to slice it right there, I've got this finger reflecting that finger. Not the same. Slice it here? No. Slice it. There's no way to slice it. There's no way to slice this thing such that the one half reflects the other half. That means that a hand has no plane of symmetry. You take an object that has no plane of symmetry and put it in front of a mirror, you see an object that is different from the original object. That's what it's all about. Don't go thinking that this is not significant. This is major. Virtually every molecule in your body, except the most dominant one, of course, is water. Virtually every other molecule in your body has this property. is a molecule that has no plane of symmetry, therefore has a mirror image that is different from itself. And it is very important which of those you're using. Let's go back to baseball, shall we? A baseball. Does it have a plane of symmetry? Sure. You could slice a baseball in half. You got half a baseball here, half a baseball here. They're going to reflect each other. So if you hold a baseball in front of a mirror, what do you see? You see a baseball in the mirror. If you were somehow able to reach into that mirror and grab the baseball, you would not be able to tell which was the original baseball and which was a mirror image because they are identical. Are they enantiomeric, therefore? No, they're the same thing. A baseball bat. If you hold a baseball bat in front of a mirror, what do you see in the mirror? You see a baseball bat. If you're able to reach into the mirror, grab the baseball bat, could you tell which was the original bat and which was a mirror image bat? No, they are identical. Why? Because bats, a baseball bat, which I will artistically draw here, has a okay, a 2-year-old wiffle ball bat has a plane of symmetry. We can cut that thing in half, and the two halves reflect each other. The fact that it has a plane of symmetry means its mirror image is going to be the same as itself. A baseball glove. I'm right-handed, Teddy, so my glove fits on my left hand. If I put my glove in front of a mirror, what do I see in the mirror? I see a left-hander's glove, one that would fit on the right hand. They are not the same thing. Even though very few of you knew any professional baseball teams. This is America, for crying out loud. So I'm assuming you've all had a ball glove on your hand at some point in your lives. At some point. How sad. Anyway, you put a glove made to fit on the left hand in front of a mirror, you see a glove made to fit a right hand. They are not the same thing. Now think about this. Let's say you're a pitcher. A pitcher throws the ball. Let's say you're a pitcher. Let's say you're a right-handed pitcher. Do you need to get a right-handed ball to pitch with? Can you and your left-handed pitcher friend use the same ball? Yes. Let's say you're a right-handed batter. Your friend's a left-handed batter. Can you use the same bat? Yes. So whether you're right-handed, it doesn't matter what bat you grab. Whether you're right or left-handed, it doesn't matter what ball you grab. Does it matter what glove you grab? Yes. So the whole idea here, a pair of enantiomers are going to be identical in all chemical properties. Everything they can do. They're going to burn equally. They're going to have the same melting point, same boiling point. They're going to react with the same things. They're going to be absolutely identical in everything except for their ability to interact with other enantiomers. That's the only time enantiomerism even matters. You have a pair of molecules that are mirror images of each other. They're going to be absolutely identical in all chemical properties except when interacting with other enantiomeric molecules. In other words, my enantiomeric pair of hands, identical in interacting with a ball, identical in interacting with a bat, identical in interacting with a pen. I don't need to get a separate pen if I want to write left-handed. Not identical when interacting with another set of enantiomers, like a pair of gloves. If I want my left hand to interact with the glove, it needs to interact with only one of that pair of enantiomers. It can interact with one of them, it cannot interact with the other. Does that make sense? Of course it does. Chemistry always makes sense. So enantiomerism is completely irrelevant in everything, unless we're talking about something that is enantiomeric interacting with something else that is enantiomeric. Well, guess when that happens? When do enantiomeric things react with other enantiomeric things? Like virtually every chemical reaction that has ever occurred inside any biological entity, as one example. So don't go thinking it's not important. It only matters enantiomer to enantiomer, but that situation is common. Okay, so it's worth, and let me write that down, that enantiomers have identical chemical properties except for their interaction with other enantiomers. Famous example of not appreciating the difference in interactivity enantiomer to enantiomer is this comes up in a lot of classes, comes up in a lot of social science classes, but the substance thalidomide. Anyone heard of thalidomide? It was used a lot in the late 40s, early 50s, primarily as a relief for morning sickness for pregnant women. And then all of a sudden, the incidence of deformed babies, especially babies born with shortened, malformed appendages, arms and legs, started cropping up. I was born in '54, so I feel like I dodged that bullet. Mom didn't take thalidomide. Yes, Mom, thank you. But anyway, essentially what had happened is when thalidomide was first studied as a morning sickness thing, they were studying a particular enantiomer of it, and it was quite effective. When they put it out for mass production for people to use, it is very, very expensive to separate a pair of enantiomers into their, the object in its mirror image. So most things that have no plane of symmetry are usually sold as a mix of the two enantiomers because it's a whole lot easier to produce that. So that's what was sold, a mix of the two enantiomers of thalidomide. Well, the one enantiomer relieved morning sickness, the other enantiomer caused all these birth defects. Amazing, that would never happen these days. We're way too aware of that potential. It's even amazing to me in the 40s that was allowed to happen, that someone didn't step up and say, hey, we need to study this other enantiomer before we start giving it to people. Anyway, that's a famous example of kind of not paying attention to the fact that a pair of enantiomers can have very different properties when interacting with other enantiomers, which is virtually every biological reaction ever. Okay, here's another statement. We're not going to get into this yet. We will tomorrow. Enantiomers have identical physical properties. A pair of enantiomers, boiling point's the same, melting point's the same, water solubility the same, color the same, everything the same. Physical properties have identical physical properties except for their ability to rotate the plane of plane polarized light. Now I suspect that makes no sense whatsoever at this point, but we will make sense of it. Give me a minute, I'm going to go and molecule out of the room. So their physical properties are identical except for the ability to rotate the plane of plane polarized light. We'll talk about plane polarized light tomorrow. I will just say now that you all know what it is. You've all experienced it. You probably don't know that you know what it is. And even though you've experienced it, you may not know really what it is. But I know you've experienced it. Okay, so hands and bats and balls and gloves and everything, that's cool. Yes, my favorite sport is baseball. Yes, if you want to get on my good side, we can talk baseball. What does all this have to do with molecules? Organic chemistry, carbon, yay carbon. sp3 hybridized carbon, tetrahedral geometry, there you go. There's a carbon with 4 things bonded to it. If I hold this in front of a mirror, that's what I see. Carbon enantiomers? They're mirror images of each other. Carbon enantiomers? They're the same thing. I pull this out of the mirror, I try and line it up with this guy, I can totally, completely line it up. Which was the original molecule? What was the mirror image? You can't tell. They are identical. They're not only not enantiomers, they're not isomeric at all, they're the exact same molecule. And we could have predicted that because this thing has a plane of symmetry. I could take this molecule, slice it right through the white ball, right through the black ball, right through this white ball, and the 2 halves reflect each other. It has a plane of symmetry. I can slice it and the 2 halves are going to be mirror images of each other, going to reflect each other. So the fact that this thing has a mirror image, has a plane of symmetry, tells me that its mirror image is going to be the same as itself. Well, what if all 4 things weren't the same? Let's replace a white thing with a green thing. If I hold this up to a mirror, I'll see this. So these guys are mirror images of each other. Are they a pair of enantiomers? No. I could pull this thing out of the mirror and I could line it up part for part. White guys with white guys, green guys with green guys. They are identical. And we could have predicted that because this molecule has a plane of symmetry. Right through the green ball, the black ball, the white ball, slice it right in half, the 2 halves of this molecule will reflect each other. What if I put a red guy on here? Let's say I hold this up to a mirror. I would see this. Red guy reflecting red guy, green guy, white guys, white guys. Are they a pair of enantiomers? No. I can yank this guy out of the mirror and I can line it up part for part. Here I have the white guys lined up. I turn it over this way. You can see I have the red guys and the green guys lined up. They are absolutely identical. And we could have predicted that because this thing has a plane of symmetry. I can slice it right through the red ball, the black ball, the green ball, and the two halves of the molecule reflect each other. Let's put a blue guy on here. If I hold this up to a mirror, I've got this guy. Red guy reflecting red guy, blue guy, green guy, white guy in the back, white guy in the back. So they are mirror images of each other. Are they a pair of enantiomers? Now they are. If I try and yank this guy out of the mirror, I can't line them up. I can line up, the red guys and the blue guys, but then the white guys and the green guys are exactly inappropriately aligned. Sure, I can make the, of course I can, because I'm coordinated. I can make the white guys and the green guys line up, but then the red guys and the blue guys aren't lined up. These are distinctly different molecules. And we could have predicted that because we look at this, it has no plane of symmetry. There's no way to slice this so that the one half reflects the other. If I slice right through the middle of the red, black, and blue balls, then I've got white ball on one side, green ball on the other. No matter how I hold it, no matter how I slice it, can't be done. The lack of a plane of symmetry necessitates a mirror image that is different from itself. So when it comes to organic chemistry, you got to have yourself an sp3 hybridized carbon. So right away, if we're talking about an sp2 or sp hybridized carbon, you're not going to have an enantiomerism. It's got to be an sp3 hybridized carbon, tetrahedral geometry, and all four things bonded to that carbon must be different. That's when you can get an enantiomerism. If you have a carbon that has four different things bonded to it. Such a carbon is called by a variety of names. If you have a carbon with four different things bonded to it, it's called by a variety of names. It's sometimes called a stereocenter, because it's a center of stereoisomerism. That's a logical name. It's sometimes called a stereogenic carbon. The suffix there, genic, gen, having to do with birth, origins. So, origin of stereoisomerism, if you have a carbon with four different things bonded to it. It's also commonly called a chiral carbon. Please pronounce that correctly, chiral, not chiral. Chiral, a chiral carbon. And that comes from the word chirality, which comes from the Greek, and it literally means like a hand, or handedness. Something is chiral if it is like a hand. In this sense, like a hand, in that it has no plane of symmetry and therefore has a mirror image that's different from itself. So anything that fits into that category can be said to be chiral. Hands are chiral, by definition. Gloves are chiral. Carbon-based molecules that have four different things bonded to a carbon are chiral. a minute left. I gotta do something with that minute. Here's what I'm gonna do with that minute, and that's one question. That's one question. We had isomers, constitutional isomers, stereoisomers. Stereoisomers, we had enantiomers, diastereomers. Where does cis trans guys fit? You had three choices. More specifically, they're diastereomers, or diastereoisomers, both, exactly. Cis trans guys are not mirror images of each other. They're stereoisomers, but not mirror images of each other. They're diastereomers. There are only two types of diastereomers we're going to talk about. Cis trans and the other.